Video's isotopes. The essential questions are: what is an isotope? Why do the masses on the periodic table have decimals? And how do you find an average atomic mass? So an isotope is an atom that has the same number of protons but a different number of neutrons. So it'll have the same atomic number, which is what identifies the element, but it can have different mass numbers. And you remember that from atoms in a bag. We had some that were the same element, but they had different masses. On the bottom of the page here, we have an example with sodium. On the left, we have 11 protons, which makes it sodium, 12 neutrons, which, remember, to get the mass number, you add protons and neutrons, so this makes it sodium 23. On the right, we still have 11 protons, which means it's still sodium, but now we have 13 neutrons, which makes it a mass of 24. So we have sodium 24. And if you also remember from our atomic structure unit, when we write these symbols, we put the mass number little up above and then the atomic number little down below. So we have 23 over 11 on the left, and that's Na. And then the isotope on the right is 24 over 11. Some more examples of isotopes. We have carbon, which is 12 over 6, 13 over 6, and 14 over 6. We have 3 different isotopes there. They all have 6 protons, which makes them all carbons. And remember, to get neutrons, we can just subtract the atomic number from the mass number. So the first one here, we have 6 neutrons, we have 7 neutrons, and then 8 neutrons. And sometimes these are considered radioactive parts of these if they're not very stable. We also have hydrogen isotopes. They all have 1 proton. That makes them hydrogen. So we have 3 different versions here. So again, we have 0 neutrons on the first one, 1 neutron on the second one, and 2 neutrons on the first one. And these all occur naturally. Okay, so this first one is called protium. The next one is called deuterium. And the last one is called tritium. And you can use that to kind of remember, if you look at the mass numbers here, protium would mean 1 proton. Deuterium, dew means 2, so you have mass number 2, and tritium, tri, means 3. So to find the average atomic mass, that's the weighted average of the mass numbers of the isotopes of an element. So they look at what occurs naturally of all the different types of isotopes, and then they take an average. Okay, but they take into account if there's lots of one kind and not very much of another. And that's what you actually see on the periodic table, and that's why there are decimals on the periodic table under the mass. Okay, because it's an average. You can't actually have an atom with a decimal number in the mass because you can't have a partial neutron or a partial proton. So for instance, it will take C12, C13, and C14, which was our carbons that we just were talking about on the last slide. And the most common is the carbon 12, but there are a few instances where you can find carbon 13 and carbon 14, and they weigh it out, and they get an average of 12.011, and that's what's on the periodic table. The average is going to be closest to the mass number of the most abundant isotope, which means the most common one, which in this case was carbon 12. With our hydrogens from the last slide, we have hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1 is the most abundant. Okay, and we know this from the periodic table that the mass number is 1.008. It's closest to 1. A mass spectrometer is a machine that does this very specifically. Okay, this is a picture of it. It's a really big machine. And it sorts atoms and molecule fragments by weight. So it will give you a printout that looks kind of like this, and you're able to tell from that what the abundance is of each type of isotope. Okay, the heaviest particles are deflected by the magnet. So this is kind of what's happening on the inside of the spectrometer. The heaviest particles are deflected by the magnet the least, and the lightest ones are deflected the most. So it's able to kind of sort them. Okay, so C12 will go over here where the lightest ones are, and then C14 will go over here where the heaviest ones are, and then C13 would be in the middle. So to calculate the average atomic mass, we're going to do a couple practice problems. For example, an element has 2 isotopes with mass numbers 10 and 11. If the percent abundances are 20% and 80% respectively, what is the average atomic mass of the element? Also identify the element. Okay, so what we're going to do is first we're going to take the mass number and multiply it by the percent. So the 10 goes with the 20%. When it says respectively, that means it's going in the same order. Okay, and we have to change 20% to a decimal, which means we slide the decimal place over 2, so we get 0.2. So we're just going to multiply those two together. Then we add the next one. So we have the next mass number and the next percentage. So 11 and then 80% becomes 0.80. Okay, so we're going to work that out. That becomes 2, and that becomes 8.8. And we're still going to add, and we get 10.80. And if we look on the periodic table, 10.80, the mass would go with boron. So this is where we get the decimal number for boron. 20% of boron has a mass number of 10, 80% has a mass number of 11, and so they add that together and they get the 10.8. Okay. 77.35% of the atoms of an element have a mass number of 35. The rest of them have a mass number of 37. Calculate the average atomic weight and identify the element. Okay, so remember again, changing the percentage to a decimal, you move the decimal to the left twice. So if I have 77.35, it's going to become 0.7735. And then all I have to do, it says the rest of them, so I have 100% total, so I'm just going to subtract, and I get 22.65 will become 0.2265. Okay, if you still had a small number, if you had a small number like 7.43%, you would still move the decimal 2 places to the left and add a 0 in the gap. So 7.43 would become 0.0743. All right, so in this situation, we have 35 goes with the 77%, so we're going to multiply those two together. And then we add the other one, which is 37, and its percentage, which is 0.2265%. So we're going to multiply first and then add. So we multiply that out, and we get 27.0725. And we get 8.3805 over here. And we're going to add those together, and we get 35.45. And when we look that up on the periodic table, we get chlorine. So again, this is how this has been calculated. And it's also a kind of a cool deal. You can use the mass spectrometer. It'll get the weights of something, and you can use it in this way to identify a substance if you don't know what it is. And you can see that on the periodic table that matches the atomic mass. Alright, this is a little bit of a challenge problem. It says 50.69% of the atoms of an element have a mass number of 79. 49.31% of the atoms have a mass number of 81. Calculate the average atomic weight and identify the element. Okay, so we have 79 times its percentage, 0.5069, plus 81 times its percentage of 0.4931. So I'm going to multiply 40.0451. And multiply there, 39.9411, and then we add those two together. I get 79.99, and if I look that up on the periodic table, it's going to be close to bromine. There's 79.9 right there. Okay, this is our challenge problem. Gallium has two isotopes, gallium-69 and gallium-71. If the average atomic mass of gallium is 69.72, we want to figure out what percent is the 69 and 1% is the 71. So that's my answer, 69.72. So I'm trying to work backwards here. So I'm going to make 69 times x, because I don't know what the percentage is, so I'm going to make that x, just like in algebra. And 71 is going to be 1 minus x. Remember, we have 100% total. So, but if we change it into decimal form, 100% becomes 1. So I'm going to have x, and then the leftovers, which is 1 minus x. Okay, so now I can solve. The first thing I'm going to do is distribute there on the right. So I have 69x plus 71 minus 71x. Now I need to collect like terms. So I'm going to subtract 71 on both sides, and I get negative 1.28. And then I'm going to do the 69x minus 71x, and I get negative 2x. I just have to divide both sides by negative 2. and that's going to give me 0.64, which if we reverse that decimal, it's 64%, and that went with the 69 mass, so that's going to be gallium 69. And so then I know the rest of my 100% is going to be gallium 71. So I just have to subtract that from 100%, and I get 36% of gallium 71.